Hello everyone, my name is Richard Teague and I'm an SMA Fellow at the CFA. Today I'd like to present to you some work done as part of the MAPS collaboration in which I look at the disks around HD 163296 and MWC480, searching for signs of dynamical interactions between the disks and embedded planets. Now we're all acutely aware that ALMA has transformed our view of the planet formation environment, and I think this gallery of D-sharp sources nicely demonstrates that. We found that every source that we look at with sufficient angular resolution and sensitivity shows a stunning variety of substructure in a continuum, most notably gaps and rings, but also in some cases spirals. These are all highly indicative of a dynamical planet formation environment and highly suggestive of a population of embedded planets sculpting these dust distributions. Now in parallel, ALMA has also allowed us to much better characterize the molecular emission coming from these sources. And in particular, this has allowed us to really start studying in great detail the kinematic structure of them. This image is showing the 12CO emission from HD 163296 taken as part of the D-sharp survey. And this map is showing the line of sight velocities. So this dipole pattern with the red shifted and blue shifted side is characteristic of rotation. What I really wanted to highlight with this figure was the size of these disks in the gas compared to their continuum substructures. So while the continuum in this particular disk extends to about 1 arcsecond in radius, the gas extends 4 times further and it's much larger. So if we really want to characterize the full planet formation environment, we really need to look to the gas. In particular, what's really great about ALMA is that it allows us to measure the velocities to an extreme precision of tens of meters per second. This allows us to search for the signs of embedded planets influencing the dynamics of their parental disk. This is what we're showing here on this figure to make some predictions for what we should look for. The simulation basically takes a smooth disk, injects 3 planets of around Jupiter mass in it, and sets it going. The left-hand panel shows the gas surface density, where the planets excite spiral waves which shock the background disk and open up gaps. These features that we see in the gas density are mirrored with similar perturbations in the gas velocity structure, here measured as a fraction of the background rotation speed. The gaps are traced very well by changes in the gas rotation because of the change in the pressure gradient that the gas feels. Similarly, along the spiral arms and spiral wakes, we see very large velocity perturbations, between 5 and 10% of the background velocity component, meaning that these signals should be screaming in the ALMA data. They should be very easy to detect. The way that we look at this is we have to explore the channel maps, and this was actually how Christophe Pant found a planet in HD 163296 a couple of years ago. These are examples of the channel maps taken as part of the MAPS data for HD 163296. In every channel, we're looking at a very specific velocity, and the emission that we see in that channel will only arise from the disk where the projected component of the disk's rotation equals that velocity. So to flip this on its head, when we look at a channel map and we see some structure in the emission profile or the emission distribution, we can attribute that structure to changes in the velocity distribution of the disk. As I said, this is what Christophe did a couple of years ago to identify a planet. He looked at this particular velocity that I've shown in the top left, which shows a very distinctive thunderbolt or kink-like structure. This, he was able to argue, was down to an embedded planet creating very large velocity perturbations and then driving very large differences in the emission morphology in that particular channel map. If you look at the opposite side of the disk, where I've got the channel on the far right, you see no sign of a similar sort of kink-like feature. It's very smooth and arc-like. So this suggests that the velocity deviation is very localized, and Christophe was able to identify the location of the planet that was able to best reproduce that kink that we saw. And that's what I've drawn in this blue oval here. Now we want to go back to this planet with maps, and because we have higher spectral resolution and slightly deeper observations, we wanted to see what we could see. And we looked at it in a slightly different way from just the channel maps. We looked at the residuals in the rotation maps. So in the left column here, I'm plotting the rotation map. So again, this is a line of sight velocity from the molecular emission. To this, we can fit a Keplerian model. So this is assuming that the gas is in purely Keplerian rotation. And we can subtract this background model to leave some residuals and see how the gas is moving relative to that expected Keplerian rotation. The difference between the two rows are different data sets. The top row is showing the data from the MAPS project, so this is slightly higher velocity resolution and deeper data, but not as high spatial resolution as the D-sharp data in the bottom row. But what's really stunning when we compared these two data sets is that the residuals looked extremely similar. The D-sharp does suffer from channelization effects due to the lower spectral resolution of the data, so this is the spoke-like features that you're seeing in the residuals. But by and large, the structures that we're seeing are very similar between both data sets. This is suggesting that we're hitting a confusion limit in terms of what we're able to extract from the data, that this is the true velocity surface that we're seeing, and we're no longer dominated by noise or imaging issues. Because we have a good idea of the 3D structure of the disk, we're able to deproject these residuals into a face-on view. Here, the disk is rotating in a clockwise fashion, and you can see that this entire surface of the disk is dominated by these sort of kinematic substructures. I've plotted a representative beam in the bottom right of this figure to show that while these structures are relatively patchy, they extend over spatial regions far bigger than the size of the beam, so we do believe that they are real structures. And we can include some annotations to guide the eye, but one of the most prominent features we see is this large arc in the top right of the disk. And so this is the kink feature that Christoph previously identified that was due to an embedded planet. What's really striking here is that this feature is much, much larger than we previously thought by just looking at the channel maps. Not only does this broad region extend over almost a quarter of the disk's azimuth, we see a very faint spiral coming from either end that extends almost a full azimuth of the disk. This is really exciting because it gives us an opportunity to go back to our models of planet-disk interactions and test whether the planets are able to reproduce such large features that we're seeing on the disk. We additionally find another strong feature, a slightly smaller radii, shown by this second dashed box. This is coincident with the gap seen in Continuum at 145 AU. And again, this is very indicative of an embedded planet, and we see a similar feature in the 13 CO emission. However, the coincidence in azimuthal location between these two planets is somewhat circumspect, so we have to go back and really try and see if we can disentangle a single planet causing both of these features and two individual planets. Again, what I really want to stress is that the power of the gas is we're tracing regions of the disk that you just can't access through continuum observations. Here on the same scale, I'm plotting the continuum observations from D-sharp, and here I've overplotted the big spiral feature that we see for the outer planet detected by Christoph and its orbital location. And you can see that's far away from the continuum, and there's no way that it would ever detect something there in the continuum. We have to move to the gas. So I think these sort of kinematic searches for planets are really going to be the way that we're going to detect the planets most likely or most easily followed up in, say, infrared observations. So in addition to HG 163296, I also looked at MWC480, and this really showed an incredibly complex gas structure, showing a huge amount of features. Here I'm showing the channel maps again, and you can already see in these channel maps there's a lot of substructure going on. In nearly every panel you can see that the emission is bounded by these little spoke-like features emanating in line wings. And this is indicative of a very complex background velocity structure. Playing the same game as we did for HG 163296, we can fit a Keplerian rotation map to our rotation map that we derive observationally, and then look at the residuals. So in the central panel, I'm showing the projected residuals that we see, and then in the right-hand one, I've managed to deproject that into a face-on view. So for this particular disk, the disk is rotating counterclockwise. You can see that here, the residuals are dominated by this large ring at around 1.5 arc seconds, but you do see concentric rings of velocity perturbations at larger radii and inwards. So this is a really complex structure compared to HG 163296 that seem to have very localized spirals. MWC480 seems to have something that's influencing the entire surface of the disk. A similar level of complexity is seen in the gas temperature. Because we're observing optically thick CO emission, we can use the peak brightness temperature as a measure of the local gas temperature. And this image on the left is just plotting the local gas temperature, and you can already see that there we have this annular sort of ring-like structure, where we see deviations of around 5 Kelvin in the gas temperature. This is for 12CO, but we see a similar sort of annular structure in both the 13CO and C18O emission, which suggests that we have very large perturbations in the gas structure of the disk. Now, what's super interesting about MWC480 is that by having annular structure in both the velocity and the temperature, we can start to see a lot of structure and a dependence on where these features are in radius. So here in these top two panels, I've taken an azimuthally averaged profile of the rotational velocity and the brightness temperature. To both of these, I've subtracted a smooth background model from it in order to highlight the perturbations that we see, and I've then located the peaks of these perturbations and the troughs of these perturbations. In the bottom panel, I've plotted the size of these perturbations, so either the peak to peak or the trough to trough ratio, as a function of where they are in the disk, and you can see this strong linear trend for both of them. This really suggests that whatever is driving these perturbations are influencing the whole disk, and it's going to be sort of the dominant instability or dynamical process that affects the entire structure of MWC480. In addition to these annular structures that we see in MWC480, we also see a stunning amount of azimuthal structure. If we subtract an azimuthally symmetric background model for the gas temperature from the map that I previously showed, you see this stunning array of azimuthal structure characterized by tightly wound spirals. Again, these spirals are consistent with the rotation direction, and if we were to zoom in a little bit and overlay some spiral arms, you can see that it's really quite a complex structure that lies on top of this azimuthally symmetric annular structure we already saw. So we can see that we see large velocity deviations with a focus at 1.5 arc seconds. We've also seen these very tightly wound spirals in the gas temperature, all emanating from roughly the same radius of 1.5 arc seconds. We also see a very tentative gap in the continuum emission out at 1.5 arc seconds, shown in the top left. And so it's very likely that a Jupiter mass planet would be able to account for all of these observed features in both the gas and the dust. However, we're going to have to follow this up with some more modelling to really confirm the presence of a planet in this disk. So just to quickly sum up, with the MAPS data, we've been able to explore these two disks, HD163296 and MWC480, in great detail and characterize their dynamical structure. For HD163296, we see a very complex velocity substructure around the outer planet previously detected, and we see strong evidence for a second planet at 145 AU. In MWC480, we see a very strong substructure characterized by spirals and angular rings in the gas temperature, and similar rings seen in the velocity structure. Here we think these can be best explained by a planet at 245 AU, however we're going to have to use follow-up observations to confirm this. Thank you for your attention.